So if you're writing it out this way, if you find that the first derivative is 0 and the second derivative is less than 0, means it has to be like this, right? Somehow. So you can say it's a maximum value. Oops. And then the opposite of that, if this is 0 and f double prime is greater than 0, then minimum value at x equals c. Again, from the picture, I think don't necessarily try to memorize all these things, but if you think about the picture, it kind of makes sense. Right? If you know that that's a place where the first derivative is 0, so if you know you have a horizontal slope there. One little disclaimer here, like some conditions apply. See store for details. Doesn't work if what's true? It doesn't work if, it doesn't work if what's true about the second derivative. If there's no second derivative, or if the second derivative is also 0, you don't know, right? Because you can have a case like that where it's a maximum. Like you can have a case where they're both 0 and it's one or the other. So you can't use it if the second derivative is also 0. Which, like think about x to the fourth. If you have a function that's y equals x to the fourth, it just looks like a parabola with sort of more flat on the bottom. If you graphed it for yourself, the first derivative is 4x to the third. Second derivative is, what is it, 12x squared. At this point here, they're both 0, right? Both derivatives are 0. So you can't use that to decide, that happens to be a minimum value, but you can't use this second derivative test. You could have made this negative x to the fourth and it would have looked like that, right? No, if it's just x to the fourth, it doesn't have... you're thinking of polynomials having the same number of bumps as that's the kind of the most they can have. If you added some other terms here, like plus 3x to the third and all that stuff, that would make it look more like what you're used to. But if it's just one term like that, basically any power function that's even looks like x squared, except the higher that even power, the kind of the flatter on the bottom it is. And any odd one kind of looks like x cubed, except the same thing, it's flatter in the middle. Anyways, that's kind of the bulk of what's in here. Giving you a bunch of questions. Maybe if you look ahead here, this is the kind of table that might be useful to analyze some of these functions. I want you to find your own way to work with this, like when you're doing some of the ones back here. What we did last time is made a table like that to help analyze something. I think that's a good way to organize yourself. You could make the other way, or in addition to, is to kind of make a number line. Whatever works for you. For this first part here, I haven't asked you to look at the second derivative yet. You can if you want while you're doing it, but find the critical points of this. To find the critical points, you got to look at the first derivative. If it's a polynomial, you're never going to have to worry about whether it's undefined or any of that stuff. I would like you to work on this, check answers. Did I give you the answers to this section? I don't think I did I?